Hey everyone, welcome to my very first devlog. In this video, I'll be sharing all the progress I made so far on my game and the engine behind it. For this project, I decided to go with C++. It gives me full control over memory management, performance and low-level system access, exactly what I need for building a custom game engine. Okay, to build this engine, we need graphics. To have graphics, we need graphics API. There are so many graphics API in the market, and I chose to go with Vulkan because it gives me low-level control, high performance, and support for modern features like ray tracing. And I chose Win32 API for Windows and input management. With Vulkan chosen as my graphics API, the first step in setting it up is creating a Vulkan instance. The instance is the foundation of any Vulkan application. It connects our application to the driver and initializes everything we need like extensions and layers. One of the layers is validation layers. Validation layers are Vulkan equivalent debugger. This helps catches error early by providing detailed debugging messages, which is really useful when working with a low-level API like Vulkan. Once the instance is set up, the next step is picking a physical device. Unlike other graphics API, Vulkan doesn't just assume a default GPU. We have to manually query all the available GPU, check their capabilities and select the best one that fits our needs. After choosing a physical device, we need to create a logical device. The logical device is what we actually use to interface with the GPU. This step involves selecting the right queue families for graphics, compute and presentation, and enabling any necessary device feature like ray tracing or anisotropic filtering. With the logical device setup, the next important concept to understand in Vulkan is queues. In Vulkan, operations like rendering, compute processing, and memory transfers are submitted to queues, which are managed by GPUs. Unlike older graphics API where everything runs on a single queue, Vulkan allows us to use multiple queues, improving performance by distributing work efficiently. This means we can run graphics, compute, and memory operation in parallel, making better use of the modern hardware. With the logical device ready, the next important step is setting up the swap chain. The swap chain is responsible for presenting image to the screen. It manages the frame buffer that gets displayed. This step involves choosing the right surface format, presentation mode, and image count to ensure smooth rendering and minimize screen tearing or latency. With the swap chain setup, the next major step is creating graphics pipeline. The graphics pipeline is a series of fixed stages that process vertex and fragment data, transforming raw geometry into a final rendered image. Unlike traditional APIs, Vulkan requires us to explicitly define the entire pipeline upfront, which gives us more control but also makes setup more complex. Each stage in this pipeline has a specific function. As you can see, the stages that are marked in green are known as fixed function stage. These stages allows you to tweak their operation using parameters. On the other hand, the orange color stages are programmable. This means we can upload our own custom code to GPU to modify how vertices and fragments are processed. These stages allows us to implement things like custom lighting models, real-time reflection, and even ray tracing. But before we can use a graphics pipeline, we need to set up render pass. A render pass in Vulkan is actually render target. Unlike other APIs where render targets are set directly, Vulkan requires us to define the entire process in advance. Every render pass consists of attachments, which are different image buffer we render to. This includes color attachment, the final rendered image, depth attachment used for depth testing to determine which pixels are visible, stencil attachment used for effects like masking. Finally, we have to set up frame buffer, command pull, semaphore and fence. I spare you the detail. And finally, we can get a triangle. At this point, we have a vertex buffer and index buffer setup, which means we can send geometry data to the GPU efficiently. The projection matrix is also in place, transforming our 3D scene into a proper perspective view. To ensure correct object visibility, we implement a depth buffer which prevents object in the background from being drawn over closer one. Additionally, to enhance realism, we introduce a simple lighting model. Now, with everything coming together, we finally have a working scene. Now that we have a properly rendered scene, it's time to take things a step further. Right now, everything is static. Objects don't move, collide, or interact with the world. That's where the physics engine comes in. A physics engine is responsible for simulating real-world interaction in a virtual environment. This means handling collision, gravity, forces, and constraints to make objects behave realistically. Now that we applied rigid bodies, our objects finally have mass, velocity, and acceleration, meaning they can move around in the scene. But there's a problem. They pass right through each other. That's because at this stage, we don't have a collision detection. To fix this, we need a way to detect when two objects intersect. There are many ways to do this, but for now, I'm doing like this. Once collision detection is in place, objects no longer phase through each other, but now they just come to stop. To make collision feel real, we need to implement collision response. Instead of stopping instantly, objects should bounce based on their momentum and elasticity. This is where the conservation of momentum comes in. When two objects collide, their velocity should change according to the laws of physics. Using the impulse-based collision response, we calculate the force applied at the moment of impact and adjust the velocities accordingly. With this applied, we have a proper collision detection and proper collision response. Now that we have objects moving and colliding, there's still something missing. Shadows. Everything feels flat because there's no sense of depth between objects and the light source. To fix this, we need to implement shadow mapping. Shadow mapping is a technique where we render the scene from the light's perspective and store the depth values in a texture. During the main rendering pass, we use this depth texture to determine which part of the scene are in the shadow. To do that, we need to set up a new render pass dedicated to rendering shadows. This render pass doesn't store color but stores depth values. We attach a depth-only frame buffer which will hold our shadows. We render the scene from the light's point of view using the same geometry but without shading. Instead of writing color values, we store depth values in the special depth texture. This depth texture essentially captures how far each object is from the light. Now we take this generated depth image and pass it as a texture to the scene's main render pass. Each fragment in the final pass check if it's closer or farther than the depth stored in the shadow map. If the fragment is farther, it means the object is blocking the light, so we apply a shadow. Now with the shaders applied, we finally get real-time shadows.